So my name is Alan Bennett. I'm a brand new member. I was reminded by Russ that I'm not the newest member. He is. That's his distinction tonight. I am a retired geologist and am also what's called a guest geologist, a volunteer at the Mount St. Helens Institute. And I lead or go along with the lead guides and interpret geology on Into the Crater, Glacier Overlook, and eruption hikes. So, and I also just volunteer to spend a lot of time on the trails and such up on the mountain with the Institute, working hand in hand with the Forest Service while with the budget cutbacks and such. We're going to have a very busy season, very busy volunteer season. So I'm looking forward here to talking about the geology of Mount St. Helens. A little bit of this presentation will be local geology, mainly just Pacific Northwest geology. Plate tectonics. We'll touch basically on that stuff. What causes these mountains to be these beautiful mountains that come out on beautiful days like today? Why are they there? What makes them what is the genesis of these mountains, and that we all love, and we all hike and love. So we'll talk a bit about that. We'll go through some of the specifics about what the types of volcanoes we have here, the types of volcanic activity we have in the Northwest, and some eruptive history with more emphasis put on recent eruptive history, i.e. 1980 on. Okay? So let's launch into it now. And if anybody has questions, feel free to ask as we, I'm going to actually move this over here a little bit out of my way, just so it's not. Well, it's just easier for me to, there we go. So anyhow, I just want to say that if you have questions, just, blurt them out, let me know. And if I can't answer them, I'll find an answer for you at some point. I'll get back to you. So the geology of Mount St. Helens is actually pretty complex, and it's constantly changing. And there's the geologists at the Cascade Volcanoes Observatory, the folks at Mount St. Helens Institute, the Forest Service folks that study geology of the mountain always say that the only constant at Mount St. Helens is change. Since 1980, that mountain has been changing. And we all know that. Many of us sitting in this room probably saw it. Many of us sitting in this room probably have memories of Mount St. Helens, fond memories of Mount St. Helens prior to the eruption. I unfortunately happened to be in the Navy and never even saw a volcano until I saw that on TV one early Sunday morning, and it kind of hooked me. And I said, that'd be a cool thing to study, would be geology. So, well, here I am. I'm not a volcanologist, but I am a geologist. I didn't study, real in-depth volcanology, so I can't talk about a lot of things in real depth, but I can give you a pretty good overview, just what I've been studying for the past 4 years with the Institute. So. Okay. So is everybody familiar with what plate tectonics, the theory of plate tectonics? That the Earth is all these plates stitched together in this really cool arrangement. Then they've moved. They're constantly in movement. There's constantly plates being made at mid-ocean ridges. There are constantly plates being destroyed as they subduct under other plates and cause certain things to happen, like volcanoes to occur. So plate tectonics is one of the big reasons that we have. It is the main reason we have the Cascade volcanoes Okay. There we go. This is the plate that affects us right here. That is the Juan de Fuca plate. And that little plate right there is why we have that string of volcanoes called the Cascade Range. That ranges from Lassen Peak down in California all the way up to the furthest volcano up in British Columbia that I can't remember the name of. But all the way up through or California, the northern part of California, Mount Shasta probably being the most famous of the California. And then we got Mount Hood and Crater Lake, which used to be a Cascade volcano, is now just a big caldera because it collapsed. And all the way up through Washington, all our big five. My favorite is Mount St. Helens, and it's all because of the Juan de Fuca plate, the subduction of that plate underneath the North American plate. And that is the plate tectonics results in what we call the Ring of Fire. And I'm sure you've heard of the Ring of Fire as well. And if you haven't, basically that is the areas where volcanoes are active due to subduction of oceanic plates, big massive plates underneath. They go down underneath continental plates. And the next slide will kind of give you an idea. These subduction zones, the Cascade Range where Mount St. Helens resides, it's a good example of a fundamental concept called a subduction zone. That's where an oceanic crust, which is has denser materials. It's made up of denser rock materials. Heavier, denser materials moves along, and there's these mid-Atlantic or oceanic spreading ridges, and those are basically out in these areas here, these blue areas, and you'll see movement. These arrows point. These are spreading ridges here, where the plates. There are plates being up. There magma from the center of the Earth is being upwelled and made into more oceanic plate. It's just added to the oceanic plate, and it makes the oceanic plate move. Okay, so this Pacific plate right here is moving sort of this way, over this way, and the Juan de Fuca plate is moving towards North America. North America is kind of, it's not stable, but it's moving maybe a little less than the Pacific plate. This heavy oceanic crust, this plate, this heavy rock, is moving down underneath this lighter weight North American plate. That's made of less dense rock. So it's made of granitic rock. And that little plate, or anywhere you see a plate where you see the red ring of fire, there is subduction going on somewhere in there, where that big oceanic plate is just moving down underneath the, bear with me. Okay, so what happens here is there's that oceanic plate, heavy, uppermost part of the mantle. It's solid. It moves. It is being moved by plate tectonics and by more of it being built at these ejected or at these mid-ocean ridge, these ridges, and it can't go anywhere. It hits the lighter, more buoyant continental plate, and it just starts to subduct underneath that continental plate right there. And as it moves down, and it gets down and further and further and further into closer to the mantle, it heats up. And as it heats up, it starts to melt, it starts to off-gas steam because it's full of water because it's been in the ocean. Now it's going down and it starts to off-gas all that gas, and there's a lot of chemicals reaction that happens down and forms up these magma chambers, these large hot molten rock that just sort of developed down here as a result of that subduction of that plate underneath the lighter plate. And that off-gassing, steam and such, causes this magma to rise, and it basically forms a volcanic arc. And that volcanic arc being all of those Cascade volcanoes and anywhere along the ring of fire that we saw in the Pacific Ocean. It goes all the way around the Pacific Ocean pretty much. Does anybody have any questions? Am I explaining this well enough, or?
Is that where the earthquakes are happening out just off the coast?
Yeah, there's that new, you keep hearing about this volcano that's the newest volcano in the Pacific Northwest. That's all part of that spreading. That volcano out there is probably it's related to the overall subduction, but I think it's related more to the edge, the spreading edge of the. Now I'd have to verify that though, but don't quote me fully on that. But yeah, that's the one that's gonna erupt the soonest, and we probably not gonna have Mount St. Helens go off anytime soon. So everybody asks me up on the trails when I'm talking to visitors, is the mountain gonna erupt today? And I go, no, the mountain won't erupt. Well, how do you know? I says, well, I'll bet you my volunteer paycheck that the mountain is not going to erupt today. Okay, I'll buy that. So anyhow, that's what we have, this magma rising. That magma is nothing more than molten rock, and when it's magma when it's underground, it's referred to as magma. When it's expelled onto the surface, it's referred to as lava. So lava and magma. So they'll get we got the subducting slab going down. It's forming the lava down here. It's, this magma. This magma starts to collect, starts to differentiate into, chemically differentiate into certain types of rocks, certain types of magma that's going to produce a certain type of lava when it gets to the surface. And it'll accumulate at the base of the crust. It'll move up and it'll take different conduits. There'll be a shallow magma storage area. That's what happened with Mount St. Helens. Mount St. Helens started getting that really huge bulge on the side of it just before it erupted, before they had the massive landslide. That bulge was growing like 4 to 5 feet a day outward, and that was part of the result of magma upwelling and coming up into a shallow chamber. A lot of earthquakes and off-gassing and all kinds of things. Mount St. Helens is the most actively monitored volcano in North America. There are other volcanoes all over the world that are actively monitored as well, but in North America, it's one of the most actively monitored. There's probably something like, I think, 56 or something different stations up there. I don't remember the exact quote, of different types of stations, seismometers, gas, GPS, gas sniffers to tell if there are changes in what's being off-gassed by the volcano, and so it's very well monitored. So if we think anything's going to happen, they're going to know quite well in advance. So, the type of volcano that's in that is in the Cascade Range, and anything pretty much formed by the Ring of Fire, is referred to as a composite or a stratovolcano. And they're typically very steep-sided from the repeating layers of lava that come up and they're ejected and are either ejected or are just forced up. And it just builds up. So it's this composite mix of different types of lava, different types of rock that's just moved up, and it makes into forms these big, beautiful cones. Like you saw Mount St. Helens before it erupted, and they referred to it as the Mount Fuji of America because it was such a perfect symmetrical cone, just like Mount Fuji. So I've only ever seen it in pictures. But and then there are shield volcanoes, and these composite volcanoes or stratovolcanoes. They're some of the biggest, volcanoes or some of the biggest mountains on the planet. There are volcanoes in Chile that are like 23,000 feet tall, and again, Mount Rainier is the largest one in North America, even though like Denali is a much higher mountain at 20,000 feet. It's not a volcano. It's a granitic batholith. It's a pluton that formed, like the Sierras. Mount Whitney is that tall, but they're not volcanoes. They were formed by volcanic processes. 80% of the Earth's surface is volcanic related in some manner or fashion. So shield volcanoes are built up almost entirely of very fluid lava flows. Think Iceland, think Hawaii, where that stuff's just blowing up into the air. It's really pretty at night when the red basalt lava is coming out. Real thin lava that just comes out and flows really, really easily, right? Well, Mount St. Helens is not like that, or composite volcanoes are not like that. But these shield volcanoes grow and grow and grow, but they don't grow, they grow out, because all that stuff comes up, the lava comes up, the magma comes up, becomes lava, and it goes out, and they're huge, cover huge areas, but they're not as high. So like every Hawaiian volcano, or every Hawaiian island at one point was a volcano. It's a shield volcano, basically. And that is basically just going over a hot spot in the oceanic plate. That plate moves, and it formed the Hawaiian chain. Every time it moved, it would form a little volcano, basically. So shield volcanoes are very massive. Again, the Hawaiian Islands, and the world's largest active volcano, Mauna Loa. And in California, Oregon, and Washington, we have a lot of shield volcanoes. You can't look around anywhere and not see some evidence of volcanism in the Pacific Northwest. If you go down to Newberry Crater, you go to, you ever been out to Marble Mountain Snow Park in the winter? I mean, you stand right there. That's right near Mount St. Helens, but Mount St. Helens isn't the closest volcano. Marble Mountain is the closest volcano, and it's this old shield volcano. It's really, really old, but it is a volcano. It's gone. It's extinct, but it's the core of an extinct volcano. And there's a whole line of them that goes to the southwest. So there are volcanoes all over the place. I mean, you probably, if you drive north from here on the 5, you'll see evidence through Kelso. You'll see evidence of there's a big hillside there. It's got some bolts and stuff into it. That's all volcanic. Big old. I think it's part of might be part of the Columbia River basalts, but I'm not positive. But where we hiked down in Silver Falls, all of that we hiked on was all Columbia River basalt, volcanics, but not associated with Mount St. Helens or the Cascade Range. They were flood basalts. That dark rock we walked on, and everywhere we turned it, it was all volcanic. So I thought somebody, a group this age would appreciate this. If I were to show this to like millennials or Gen Z, they wouldn't get it. So selling them again at Fred Meyer. Yeah, my granddaughter has one. She has one, yeah. So she would understand. But yeah, that's how I tell you. That's how you remember magma and lava. So Bad joke, I know. Sorry. Just to give you kind of an idea about the history of the eruptions in the Cascade Range in the United States. It's not, they don't take it up into Canada. But if you look, Mount St. Helens, over the past 4,000 years, has been the absolute most active volcano, right along with Mount Rainier. And, you know, so there's some sleepers out here. But, yeah, Mount St. Helens, our mountain is the most active and probably the most, you know, it might be the next one to go. Who knows? I hope to be able to see it again. I mean, and not on the proportion, you know, that it went in 1980. I would love to see another 2004 to 2008 dome building. I would love to see that, just because I'm a geologist. It interests me. So.
Get some movie footage.
What's that?
Movie footage. Get some.
Oh, it won't bother us. I just like to see, you know, smoke coming up and. Bruce.
Using that chart, they predict which one is most likely to erupt again?
Not using that chart. I mean, they basically what they would use would be, there's just so many, all of these volcanoes are monitored to some point. Okay, Mount St. Helens being the most. That's what they would look at. I mean, you could probably look at, okay, in 4,000 years, it erupted every X years, right? So yeah, you might be able to make just a guess or a prediction. I would say more of a guess, you know, that, hey, it's like the Cascadia subduction, the fault they're talking about. It's 300 years overdue or something like that, you know, for an earthquake. It's supposed to go off every 700, something like that. You know, we're overdue. So earthquake eruptions and earthquakes and stuff, the prediction is not, it's not precise. It's not really super accurate. So, but they've made a lot of strides based on what they learned from Mount St. Helens, you know, on predicting why the reaction was. The way they reacted back in 1980 when it started its first in March 1980 when it started, you know, steaming and throwing out tephra and such. They based that on a 1975 eruption at Mount Baker that occurred, and Mount Baker never really developed into anything. That eruption quieted back down and Mount Baker went to sleep. So they kind of thought at the time, back in 1980, when earthquake or volcano prediction was you know, just their seat of the pants. They had like I think they had maybe at most, you could count on both hands how many sensors they had on the mountain at the time. And they weren't very advanced, not like what we have today. And so they looked at it, they said, well, Mount Baker went back to sleep, maybe that's what'll happen here. And it didn't. Anyhow, long answer. Short answer probably would be, you can make a guess.
It's not necessarily the Cascade Range, but I don't see Yosemite out there because they're Old Faithful.
Yeah.
Because, you know, it's a super volcano. So
right.
It doesn't fall in this line.
No, it is not. It actually, it's a super volcano. It's a caldera, and okay. What that is a, like Hawaii or whatever. That's sort of a hot spot in, you know, mid plate in the continental plate, and that actually was the reason that we had all those Columbia River basalt flows, you know, 15 to 17 million years ago. Was that hot spot was under Southwest or Idaho, Nevada, and in the, you know, Oregon, Washington area, and it is actually, you know, it is actually moved over and is now underneath the Yellowstone area. So it's not a function of subduction necessarily. It is more as a sort of a mid-plate hotspot like Hawaii. Okay? It's not really subduction driven. Does that make sense?
Yeah.
Okay.
So what does it mean when unfaithful is unfaithful? I mean, when she stops and she becomes more irregular.
Well, that's geysers, okay? That's actually not volcanic eruption.
Okay.
Old Faithful is there's water. The water systems under there are affected by that hot magma chamber that's down there, right? And Old Faithful will spout based on when, whatever the physics are behind that.
It's kind of like a pressure relief.
It is a pressure release, and it is predictable. Okay, they absolutely can predict when it will happen. Okay, but it's not like predicting when a volcano will go off. Does that answer your question? What's that?
Said it's also really hard water.
Oh yeah, yeah. So any questions about this? Okay. So again, beautiful mountain, nice conical shape, and then what was left? Same view, post 1980. A little bit later, because we do have some succession. We have some lupin and some other types of biologicals coming back here. So, but Spirit Lake was still pretty much totally covered when that picture was taken. So Mount St. Helens is early eruptive history, are basically into 4 stages. There's been volcanic activity up around Mount St. Helens in that area for the past 300,000 years. But most of what we see when we look out at that mountain has occurred over the past 40,000 years, and the most the actual mountain that we see now was actually built up over the past 4,000 years or so. Okay, it just kept coming up, erupting and putting out lava, and so that Spirit Lake stage was 4,000 years ago to the present, and that is where we have the most data, simply because it's the newest. It hasn't been erupted over. It hasn't been destroyed by other eruptions, subsequent eruptions, and such. So that's where we have the most data, the most geological evidence and information available to study Mount St. Helens. So this is kind of a neat. I really like this picture. This is stolen from a USGS report, but it's open source. If you look at the crater wall, and this is something that you'll see when you do an into the crater hike with Mount St. Helens Institute, if you ever want to do that, this just shows how much goes on during a volcano, over the in developing a composite or a stratovolcano. This stuff on the top up here is from the 1980 eruption, this tephra, these tephra layers. Tephra is anything that shoots out during a volcano, anything that's erupted during an eruption. That can be anything from ash, which we probably all have some experience with, especially if you lived east of the volcano back in 1980, from ash all the way up to huge boulders that were blown out during the actual eruption itself, okay? And this tephra up here, older tephra here, this 1980 tephra is on the top up here, is probably, there are some boulders and that in it. It's just a mix of a bunch of stuff, a bunch of rock, ash and stuff that was ejected, and it sort of made a big, frosted the entire mountain, and here's some examples of older tephra from previous eruptions, these white layers here, through here. Here's an old lava dome down here and a lava dome over here. On stratovolcanoes or composite volcanoes, in most cases, lava doesn't come out like it does in the volcanoes in Hawaii or up in Iceland, where you see all that nice fiery red, non-viscous lava coming out and flowing down and cutting off roads and burning up houses. This stuff is very, very rich in silica. It's andesite, dacite, not much rhyolite. There is some rhyolite in Cascade volcanoes, but these andesite and dacite are very rich in silica, and those are two types of rock, two types of lava. And the lava, the way they form is they form these domes. They just come up. It's hot magma, but it's so thick. It's like fudge, and it's just pushed up, and it forms and cools, and it forms these spires. So you've probably seen pictures of the domes, the two domes inside the crater that have formed since the 1980 eruption. There was one that was formed in 1986 to 1980 to 1986, and then another one that formed from 2004 to 2008 that you still see steaming today. Those are the eruptions. Those are how composite volcanoes typically erupt. They form this very viscous lava that forms into these rock spires and builds the mountain. Okay, we do have a period of time, and that's what these lava domes are right here. And I'll show you some more pictures I've taken from the summit that will kind of give you an idea about how some of that lava comes out. We did have a period of about 2,500 years ago on Mount St. Helens. It was called the Castle Creek eruptive period, between 2,000 and 2,500 years ago, where we did have a lot of basalt lava, and it mostly went down the east side, basalt and andesite lavas. You go into Lava Canyon, if you ever hike down through there, you see some really good examples of that basalt and andesite lavas that flowed. And you go to Trail of Two Forests. Everybody been there? They got the casts, the trees, the big trees. Ape Cave was formed by these types of eruptions, these basalt eruptions and andesite eruptions. Less silica, move a lot quicker, form these really cool formations. So that only went on for a small period of time, geologically speaking. But by and large, most of the stuff that has come out of Mount St. Helens has been this thicker, more viscous lava that forms these spires and domes, as opposed to these nice flowing lavas. Any questions? So 1980 to 2008, we're going to kind of cover that period because that was the most recent eruptive period. 1980 was just a massive blast. It started out in March 1980. Initially, it was relatively mild steam and ash eruptions, right? So it went on for several months. Then the growth of the cryptodome being those large spires of magma coming up thick, fudge-like, and they're just coming up and forming, and they're forming this dome, right? And we start having these, the side of the mountain start to bulge out, and that was from that lava magma chamber pushing lava up and building that dome out the side. And they had, on May 18th, 1980, at 8:32 a.m., they had a 5.1 earthquake, and they had a debris flow, an avalanche that occurred. That dome had just gotten too big for its pants, and it just gave loose. And it went down in 3 successive landslides. It was the biggest landslide, again, in recorded history, and it moved 0.6 of a cubic mile, if I remember correctly, of the top of the mountain, or about 1,300 feet of the top of the mountain. Included glaciers, that included rock and mud and everything, just came off in 3 successive avalanches. And they went down the North Fork of the Toutle River. They went down into Spirit Lake. They obliterated Spirit Lake, blew Spirit Lake right, all the water up out, 800 feet up onto the side of Spirit Lake, the surrounding Spirit Lake, came back down in and brought all those trees. That's how all those trees got down in there. Spirit Lake is like a third bigger, the surface area is a third bigger, and it's much shallower than it was before. It's bigger, but it's shallower than it was before that eruption. So that debris avalanche went down. It cut off Castle Creek. It cut off Coldwater Creek. It formed Castle Lake and it formed Coldwater Lake. That debris avalanche was just unbelievable. It was like nothing they'd ever seen before. And you go up there and walk today, you walk from the hummocks around the hummocks trail, or you walk up the boundary trail, and you're in amongst all that debris that comes down, that came down off the top of that. So you go up there on a hike, and anything you're walking on is probably younger than you. It's younger than me. So it's been emplaced 45 years ago. So what you're walking on is very, very, very young stuff. It's old rock, but it was emplaced 45 years ago. Everything you walk on up there, around the hummocks and up the boundary to a certain point. So if you go on my hike I'm going to lead on September 20th, I'll do a whole geo thing for you on the way up. So explain all the cool spots and all the neat stuff. So that debris avalanche, as it broke off it broke off the side of the mountain. It came down to 3 successive avalanches. It opened the champagne bottle, basically. That magma in there was just under pressure, that steam and everything like that. Boom! It set off an eruption, and that eruption, classic Plinian eruption, for 9 hours. It produced ashfall, pyroclastic flows, mud flows called lahars that went down the rivers, took out logging camps, took out trees, took out homes, took out bridges, filled the Columbia River. The drain, or the shipping channel to like from 40 feet, or I think it was at 40 feet, it filled it up to like 12 feet. It took 2 months to dredge it all out, get ships moving again. So a lot came off of that mountain, a lot. And then they've had continued intermittent dome growth, just like that one, that bulge that was coming out the side of the mountain. Well, they've had continued growth from 1986 to 1980 and 1986. More eruptions, building more domes inside the big crater. And then 2004 to 2008, same thing. More eruptions, building those domes. So there's the bulge. Again, that was growing at 5 feet a day.
Is that you under the umbrella?
No, that's not me. No. I'd be a lot older now if that were me. So this is basically a peek at what was going on. 10 seconds. The earthquake's happening. 42 seconds in, you can see that things are starting to blow down. You can see that. Where did I put my? You can see all the dust here and that from the avalanche, how it's breaking loose. There's more dust, and then now the lateral blast is coming out the side of the mountain to the northwest, causing all that damage. I mean, that debris flow went something like 11 to 14 miles down the North Fork of the Toutle River, and the lateral blast singed trees all the way down to Hofstadt Bridge. I mean, that's how far down it affected. It knocked down a lot of trees a lot closer in, but it singed them all the way down there. And then there it is, 60 seconds, pretty much full-on lateral blast, and then the classic eruption starting right there. Big mushroom cloud going up. This will just kind of give you some ideas of the impacts of the the 1980 eruption. There was the original 8,600 and change is how, 9,600 and change was how tall it was, 9,600 and a little more. That blew all off. Now it's like the crater rim, the highest point in the crater rim is just over 8,300 feet. And as you can see, here's the 1980 to 1986 lava dome from that eruption. And then there's another big one up here above it, closer to the crater wall back here. And that is the 2004 to 2008 lava dome right back there. And that is still active. There's still steam coming out of there. On a good day, you go up there, you see steam. So there's a pumice plain, the run up, this right here, the landslide deposit went down this way and then all the way down, formed the hummocks down here, just kept going all the way down. It came up, it ran up over top of Harry's Ridge, or near Harry's Ridge, and up over here, up over the Johnston Ridge area. And you can see good examples of that out on the trail to Harry's Ridge. But that's a long hike these days. Now this is what I was talking about, that dome growing. This is actually lava. This is how composite volcanoes with that thicker, heavier duty magma, that more silica-rich magma, that's how they form. These big, this was called the whale back or the whale tail, and it was just this spine that grew up, and these kept growing up and breaking off and falling over. And that's how that dome built. This stuff is hot down there, you know, in the chamber, in the magma chamber, and as it's moved up, and as it's moved up and forced up, it becomes cooler and cooler. Gets to the top, it'll break up and fall down, and continue to build these domes. So very much different than what you see in Hawaii, Iceland, or other types of volcanoes. This is a picture that I took standing on the crater rim, looking down into the crater dome, the 2004 to 2008 crater dome. So is it still active? Yes, it is. You be the judge. I see a lot of steam there. And so this was taken a couple years ago. And this is just, that's our mountain from the Hummocks Trail.
So why did it make all those humps that are the hummocks? What's entailed to that?
That's just huge hunks of the top of the mountain, right? That as they were coming down, they were being tossed and turned, and some of them were just sliding along. Some of them weren't even moved around. But you'll see when you walk through there, everything you see when you walk through the hummocks and you start to walk up the boundary trail and you look down on it, everything you see from basically from the breach all the way down is some form of what they call a hummock. And nobody knew, if you go, next time you drive north or south and go past Mount Shasta, there's hummocks everywhere, all the way out to I-5. They're all over the place out there. Nobody ever knew what they were, right? Until Mount St. Helens, and they figured this out. In fact, kind of an interesting story. I know that's probably, I'm going over time, but it's an interesting story. David Johnston, who was the geologist that was killed, lost his life during the eruption. One of his undergrad, or his graduate students working on his PhD was supposed to have been up at the mountain on the 18th, and he had to go to somewhere in, out of state to either defend his thesis or something. There was something going on. David said, "I'll go up, I'll take it for you." Well, that individual, his name's Harry Glicken, and he took it upon himself to do field research all through the debris avalanche. He figured it all out, and he's written a really good report. There's an awesome report about that, and worldwide now they have found evidence of debris avalanches associated with volcanic eruptions of composite volcanoes. all because of Mount St. Helens, really. So Harry Glick and Harry unfortunately died in 1991, in a volcanic eruption as well, studying. So. Yeah, Mount St. Helens and Mount Margaret backcountry. That's a picture I took in January this year. And Mount Margaret has its own interesting orogenesis, its own genesis story of how it was developed, and maybe we'll go into that on our walk up to the Johnson Ridge Observatory. So, igneous is bliss. I love it. Any questions or comments? Bruce?
That earthquake that set it off, is that
Yes.
a result of a fold, or is that something deeper?
It probably was part of they've been following swarms and swarms of earthquakes for quite a while, since March, and they kept getting more and more bigger and bigger and more of them. So yeah, that was probably a result of the magma chamber and shifting and such. There are reports that photographers who have taken pictures and also geologists that were looking at the mountain at the time that it blew, just before it blew. They said the mountain was out of focus. The top of the mountain was out of focus. That mountain was shaking. That mountain was like shaking really bad. and then that bulge got too big for its britches. Boom, boom, boom. It just went off. And again, on our hike, I'll show you a really cool thing, about some of the that landslide as it came down, how it was stopped, how they figured how fast it was moving in certain areas and stuff. There's all kinds of cool geological little clues up there that, if you're lucky enough to have studied it, it's pretty cool to see. So.
Most of us around here saw the Helens River.
Right.
And it was hot.
Yep.
And the fish were all dead.
Yep.
And the logs were coming. So most of us saw that. And I flew in a helicopter soon after it blew, and the logs were just like toothpicks.
Yeah.
It was really interesting. They flew over here.
Yeah, that was that lahar, and again, those lahars, those mud flows, are one of the most dangerous parts of a volcano, especially in the Pacific Northwest, and especially around Mount Rainier. Mount Rainier, they have in Puyallup, Orting, different areas southeast or southwest of Mount Rainier. The school districts have lahar drills. We have to be able to get out of here if something were to happen, if an eruption were to occur. Maybe not even a big eruption, but enough to melt one of those massive glaciers up there. It could bring down a lot of mud, a lot of water, a lot of trees, right through a very highly developed area. So those lahars were very, very destructive, taking out bridges, taking out logging camps, taking out, it was crazy. Yeah.
That's good.
Yep. Yeah. Yes, sir.
Hi, I'm Jerry Wilson, and I've been in the club for a long time. And I did some really stupid things back then. I actually climbed to the top of Mount St. Helens. You go up to the glacier, or the North Summit, and you go to the real summit, and it looks like the mountain goes the other way, kind of like recent. Like this, it goes up. So I thought, that's like a recent lava flow. You go down there and there's a lot of, like edge caves and all the gaps. Obviously there was some very much activity. And that river, I call it river, my friend went and looked at it. The mud was so thick, he said, when I went around the curve, it cracked.
Oh my gosh.
It was really thick. So
Wow.
fortunately, it didn't go with the dike. It got
Yeah, into the town. Yeah, that was massive. Yeah. Any other questions? All right, thanks, I appreciate it.